Due to COVID disrupting students' education for the 2022 summer GCSE exams, the exam boards have released an advanced notice article that gives an insight into what will be on the exams this year. I'm sure your teachers have shown you this article already. In this version of the advanced notice article, I'm going to show you anything in green is definitely going to be on the exam. Anything in yellow may be on the exam in a small way, and anything in red will not be on the exam. In this video, I'll go over the green and yellow areas to help you prepare for the Combined Physics Higher Paper 1 exam. So we know what's going to be on the paper because of this advanced notice article. In this video, I'll just be going over the higher tier. But in most cases, it's very similar to the foundation tier, as you can see here. So both the foundation candidates and the higher candidates need to know everything on here. If it's in green in this document, it'll be a major focus and will be assessed on the exam. If it's red, it'll not be assessed. And if it's yellow, anything yellow may be included as 1 or 2 marks, but it's not a main focus, or it'll complement the green areas. These codes down their sides let you know which lesson you'll find further information from the Pearson book. I've also got playlists on my YouTube channel in the Edexcel playlist where you'll find further videos that'll help to increase your knowledge. So the first unit I'll go over is actually 2 units. It's SP1 motion and SP2 forces and motion. The units are very similar. You can't really separate them. So you're supposed to be able to explain that a scalar quantity has magnitude or size, but no specific direction. Magnitude is just a posh word for size. For example, 18 meters per second. It's just got a size. Yes, it's got units as well, but there's no direction. You've got to be able to explain that a vector quantity has both size and direction. For example, 18 meters per second, north. Explain the difference between vector and scalar quantities. Well, as I've just explained, a scalar quantity has only size, a vector quantity has size and direction. That could be worth 2 marks in an exam. Recall vector and scalar quantities, including. So if I've underlined it in red, it's a vector quantity, it has size and direction. If I've underlined it in orange, it's just a scalar, it has only size. Now sometimes they can be paired up. So distance, if you give distance a direction, it then becomes known as displacement. If you give speed a direction, it becomes known as velocity. So velocity is basically speed with a given direction. Acceleration is a vector, force is a vector, weight is a vector, but mass is a scalar. Mass doesn't act in any particular direction, whereas weight always acts downward. Momentum is a vector and energy is a scalar. Recall that velocity is speed in a stated direction, as I've just said up there. Recall and use the equations. Speed equals distance divided by time, and rearrange it to find distance equals speed times by time. So make sure you've practiced those. Analyze distance time graphs, including determination of speed from the gradient. So distance time graph. Distance goes up the side, time goes along the bottom. The steeper the gradient is, it means that the object is moving faster, and if it's a flatter slope, it means the object is slower. In order to get the speed from the gradient, remember speed is distance over time, so you can see this object here has covered a distance of 20 meters and it did it in 10 seconds. So 20 meters divided by 10 seconds is 2 meters per second. This object here in 10 seconds only travelled 10 meters. So 10 meters divided by 10 seconds, and that comes out as 1 meter per second. Recall and use the equation acceleration equals final velocity take away initial velocity divided by the time taken for that change to happen. Use the equation v squared minus u squared equals 2 times by 8 times by x. So this is showing you the relationship between acceleration and distance. This equation is the relationship between acceleration and time. You need to be able to analyse velocity time graphs to compare acceleration from the gradients qualitatively, just means to work out the gradients without using numbers, and also calculate the acceleration from the gradient, so that means using numbers, and determine the distance travelled from the velocity time graph. So the velocity goes up the side and the time goes along the bottom on a velocity time graph. The slope shows us how much the velocity is changing over a given time, which gives us acceleration. The area under the graph gives us the distance travelled. So if there's uniform acceleration, the area under the graph will just be a triangle. So to get the distance, you do a half times by the height times by the base. At this point, the object is moving with a steady speed, and the area it creates under the graph is either a square or a rectangle. So to get the area of that, you just do the base times by the height. The height was 10, and the base goes from 5 to 15, which is also 10. So 10 times by 10 gives us 100. The total distance would just be, adding those two things together, 125. If we need to calculate the acceleration, you just work out how much the velocity has changed by and how much time it took for that change to happen. If it's a steep slope, it's a large acceleration. If it's a flatter slope, it's a smaller acceleration. And as I showed you here, if there is no slope, there's zero acceleration. It's a steady velocity. To calculate the acceleration, we use this equation, v minus u over t. So v, the final velocity, was 20. U, the initial velocity, was 0. So 20 take away 0. It took 10 seconds for that to happen. So that comes out as 2 meters per second squared. For this smaller acceleration, v minus u, the final velocity, was only 10. The initial velocity again was 0, and the amount of time it took was 10 seconds to change. And that came out as 1 meter per second squared. Describe a range of laboratory methods for determining the speeds of objects, such as the use of light gates. So a light gate is literally a gate with a light. If you break that light, it triggers a timer. We put a card on the back of a little trolley. If you know how big the card is, we type that into the little data logger, and as the trolley passes through, the card breaks the light, triggers the timer for a certain amount of time, and we know the distance was 10 centimeters, so you do the 10 centimeters divided by the amount of time, and that'll tell you your speed. Another way of getting the speed would just have a start and an end, measure the distance with a trundle wheel, and measure the time with a stopwatch. Make sure that the distance is nice and big so you don't have any problems starting and stopping the stopwatch in terms of human error due to reaction times. Just concentrating on the higher tier, you can see there's some significant differences here. When we get to this point, the foundation candidates don't need to know any of this stuff, whereas the higher candidates do. 12.2. Recall some typical speeds encountered in everyday experience for wind and sound, for walking, running, cycling and other transportation systems. So wind and sound, well, wind could be 4 meters per second, which is 9 miles per hour, or it could be 10 times that. If you're in a storm, 90 miles per hour would be 40 meters per second. The speed of sound is usually 330 to 340, depending on the density of the air. Walking's about 1.4 meters a second, running 4 meters a second, cycling 6 meters a second. And if you're in a car, if you're going at 70 miles per hour, which is the speed limit on a motorway in England, then that's 31 meters per second. 12.13. Recall that the acceleration g in free fall is 10 meters per second squared. So you'll get 1 mark just for knowing how big gravity is on Earth, which is this value here for gravity, 10, and be able to estimate the magnitudes of everyday accelerations. The acceleration of a person could be 2 meters per second squared, or if it's a car, 4 meters per second squared. That wouldn't be a sports car, because that would be even higher. We don't need to know any of this, and this is for higher only. Explain that an object moving in a circular orbit at constant speed has a changing velocity. Now that's because the direction is changing, of course, and velocity is a vector. It depends on size and direction. So if we saw an object moving round in a circle, at this particular moment the velocity is going upwards, and at this particular moment the velocity is going to the left. So you can clearly see that the direction is changing even if the size of the speed is not changing. So it could be a steady 20 meters per second. That would be the speed. Explain that for motion in a circle there must be a resultant force known as a centripetal force that acts towards the centre of the circle. So if you're asked about that, the centripetal force always acts toward the centre of the circle. Draw it from the object going into the centre. If the object was up here, I've shown you how to draw the centripetal force for that instance. Explain that inertial mass is a measure of how difficult it is to change the velocity of an object, including from rest, and know that it is defined as the ratio of force over acceleration. So inertial mass is force over acceleration. That's what that means. So it's basically Newton's second law, F equals ma, rearranged. Right, to create an acceleration of 2 meters per second squared, if we've got a 10 kilogram mass, that would need 20 newtons of force. If we had 100 kilogram of mass, then that would need 200 newtons of force. And if we had 1,000 kilogram mass, it would need 2,000 newtons of force. In other words, massive objects have huge inertial mass and need a massive force to get them to move, change direction, or stop. The example I like to think of is an oil tanker ship. So in order to get this oil tanker, because it's got a huge mass, it'll take a massive force to get it to move, get it to change direction, get it to stop. So we just call its mass the inertial mass. And to work out the inertial mass, you just need to know how much force is required to make it accelerate. Recall and apply Newton's third law to equilibrium situations. Basically, Newton's third law is every action has an equal but opposite reaction. So if we've got two forces of the same type acting on two different objects, then you know it's Newton's third law. For example, if a person is heading a ball, then they are putting a force on the ball. At the same time, the ball would put a force that's equal in size but opposite in direction onto the head. So you can see here, the force of the ball on the head will be 10 newtons, and the force of the head on the ball would also be 10 newtons. Recall and apply Newton's third law to equilibrium situations and to collision interactions, and relate it to the conservation of momentum in collisions. In other words, the conservation of momentum in collisions just means the momentum before equals the momentum after. To get the momentum, you do the mass 1 times by the velocity 1, and then the momentum after would be the mass 2 times by the velocity 2. But for momentum in collisions, the second mass is usually a different object, or sometimes it's two objects combined together. If you don't know what you're doing with that, I've got a nice little video in my SP2 playlist from the Edexcel playlist. To find momentum, recall and use the equation for momentum. So momentum just equals mass times by velocity, as I've said over here. Describe examples of momentum in collisions. So being able to talk about trains colliding or pool balls being broke. Again, that's in my momentum video if you need any extra help. Use Newton's second law as F equals mv take away mu divided by t. So if you're wondering where that came from, Newton's second law starts off as force equals mass times by acceleration, F equals ma, but we know that acceleration is v minus u over t. So if we just substitute a for that and then multiply everything by the m, we get mv take away mu divided by t. So this is just Newton's second law, wrote slightly different. Make sure you know how to use it. Explain methods of measuring human reaction times and recall typical results. So the way that we do that is you'd have some kind of stimulus, for example a light coming on, and then a response from a human could be to push a button to turn the light back off. The human reaction time is the time between the stimulus and the response. So the time it takes for the light to come on and for the human to press the button to turn it off, that's the human reaction time. You've got to be able to recall that the stopping distance of a vehicle is made up of the sum of the thinking distance and the braking distance. So total stopping distance equals thinking distance plus braking distance. For the higher tier, this is all yellow. For the foundation tier, it's green, and then you don't need to know that last bit there. Explain that the stopping distance of a vehicle is affected by a range of factors, including the mass of the vehicle, speed of the vehicle, driver's reaction time, vehicle brakes, state of the road, and the friction between the tyre and the road surface. If it's been underlined in red, then that's a braking distance factor. If it's underlined in green, then it's a thinking distance factor. So remember, the braking distance is the distance you travel once you've pressed the brakes on the car. The thinking distance is the distance that you travel while you're thinking about pressing the brakes. For example, if someone steps out onto the road. You've got to describe the factors affecting a driver's reaction time, including drugs and distractions. So, how long it takes the driver to react, it depends if he or she's been drinking alcohol, drugs, distracted, or if they're tired. All of those things will make the driver's reaction time increase. So instead of being able to react very fast in 1/4 of a second, it might take them 3/4 of a second instead, which would increase the thinking distance. Explain the dangers caused by large decelerations and estimate the forces involved in typical situations on a public road. Well, large decelerations can cause injury and death. And they'll usually give you some forces to choose from, and you've got to say which one seems reasonable for particular situations. And this is the last part that we need to know for the SP1 and SP2 units. Right, let's move on to the SP3 Conservation of Energy unit. You can see once again it's very similar. The higher candidates need to know all of this. The foundation candidates just need to know this here and not that bit there. And then apart from that, everything else is the same. Neither higher nor foundation candidates need to know this bit here. Recall and use the equation to calculate the change in gravitational potential energy. This triangle here means delta, which is change in. So the change in gravitational potential energy equals mass times by gravity times by the change in the height. You need to know about kinetic energy, how to calculate it. So kinetic energy is 1/2 times by mass times by velocity squared. You should be able to draw and interpret diagrams to represent energy transfers. So for example, a bulb, the energy transfer diagram would show that electrical energy goes in, turns into light energy, which is useful, and heat energy is wasted. The arrow pointing downwards is always the wasted energy. You've got to explain what is meant by the conservation of energy, which just means the energy in equals the energy out. So I've put some values on the energy transfer diagram. If 200 joules of energy goes in to the bulb, then 200 needs to come out. 70 of it was useful in this case, and 130 was wasted. Now the wasted energy still exists though, it just means that it can't be used for any further useful energy transfers. Analyse the changes involved in the way energy is stored. So if you've got an object being projected upwards, being thrown upwards, or on a slope, if it's moving, it's got kinetic energy, and as it moves upwards, it'll get converted into gravitational potential energy because it's getting higher. A moving object hitting an obstacle, well, that'll be kinetic energy because it's moving at first and then getting turned into sound energy as it hits an object, and some heat energy as well. An object being accelerated by a constant force, well, whatever energy it had, it's going to get stored as kinetic energy because it's moving. A vehicle slowing down, the kinetic energy would get converted into heat energy. Bringing water to a boil in an electric kettle, well, electric energy is going in and it's getting turned into heat energy. Explain that where there are energy transfers in a closed system, there is no change to the total energy in that system. So it just means the energy at the start equals the energy at the end. If it's a closed system, it's like being in a room where you can't get out of. Nothing can get in, nothing can get out. 3.7. Explain that mechanical processes become wasteful when they cause a rise in temperature, so dissipating energy in heat to the surroundings. What it basically means is you've got to tell the examiner that wasted energy gets turned into heat and it goes to the surroundings. Examiners like you to use the word dissipate, but it just basically means spreading out and going to the surroundings. Explain using examples how, in all system changes, energy is dissipated so that it is stored in less useful ways. So, as I say, energy is always wasted as heat. It can't be used for any further useful energy transfers. Explain ways of reducing unwanted energy transfer, including through lubrication or thermal insulation. So we often lose energy as heat because things rub together. If we lubricate or use some oil on the moving parts, that will reduce the friction and therefore it will reduce energy loss caused by heat. Thermal insulation, well, if you've got some water that's hot, that energy is going to dissipate to the surroundings, unless, of course, we put some insulation around it and maybe even a lid on the top. And that ties in with describe the effects of the thickness and thermal conductivity of the walls of a building on its rate of cooling. So if we look over here, the rate of cooling decreases, so the object stays hotter for longer if the insulation is thick and if the thermal conductivity value is low. If you're a good conductor, it means that you will allow heat to go through. So if you've got a thermal conductivity value that's low, it means you're not a good conductor, which means not much heat will pass through. In other words, the heat will stay in the object, in the water in this case, rather than passing out to the surroundings. Recall and use the equation for efficiency. So efficiency is useful energy out divided by the total energy in. Higher candidates also need to be able to explain how efficiency can be increased. Well, if we look at the equation for efficiency, if we can make the top number bigger, then that will make the efficiency bigger. So if we have more useful energy, or you could say have less wasted energy, that will make the efficiency bigger, because it means more of the energy that you're putting in is actually turning into useful energy as the form that you want out. We don't need to cover any of this. Unit SP4 Waves. You can see the higher candidates just need to know a little bit about this. The foundation candidates need to know a little bit more. And there's a little bit of difference down the bottom about who needs to know what. Recall that waves transfer energy and information without transferring matter. Well, that's just a statement that you need to know. Describe evidence that with water and sound waves, it is the wave and not the water or air itself that travels. In other words, the water simply bobs up and down. It does not move toward the shore, unless it's a tidal wave, of course. And air, well, if the air moved, instead of simply vibrating backward and forward, it would create places with no air and people would choke, which doesn't happen. So if I'm talking to you, the air from my lungs doesn't actually go into your ears. Define and use the terms frequency and wavelength as applied to waves. So frequency is how many waves there are per second. So you've got a high frequency, you'll have lots of waves per second. If you've got a low frequency, you'll have only a few waves per second, or one wave as I've showed here. Wavelength is literally the length of the wave. You can show it on a diagram going from peak to peak or from trough to trough. Use the terms amplitude, period and wave frequency as applied to waves. Amplitude just basically means how much energy the wave's got. So if it's got a small energy, it would just go from the middle section where there's zero energy, it would just go up a little bit. Whereas if you've got a large energy, then the amplitude would be big. So the amplitude, just to make it clear, goes from the middle to the top of the wave or from the middle to the bottom of the wave. It does not go right the way from the top to the bottom. Examiners might try to catch you out by adding that to a diagram and asking which is the correct amplitude. Period just means the time period for one wave to be produced, and wave velocity is basically the speed of a wave but in a given direction. We don't often quote the direction when we are talking about wave velocity though. Describe the difference between longitudinal and transverse waves by referring to sound, electromagnetic, seismic waves and water waves. So if it's a longitudinal wave, I've underlined it in red. So you've got an earthquake wave called a P wave, and you've got sound. And pretty much any other wave is transverse. So all of the 7 electromagnetic waves are all transverse, and the waves on the top of water is also transverse. Recall and use both the equations below for all waves. So we've got the wave velocity is the frequency times by the wavelength, or also to get the wave speed or wave velocity, you can just do distance divided by time, just like you can get the speed or velocity of any object by doing distance over time. They've used x for distance. Describe how to measure the velocity of sound in air and ripples on water surfaces. So again, to get the velocity, we just want to do distance over time. So the velocity of sound in air, well, you'd have to get someone to fire a starter pistol and get someone to stand quite far away, measure a large distance, because that's going to decrease the errors due to human reaction time. It'll increase the accuracy. When this person sees the gun being fired, they start the stopwatch. And when they hear the sound, then they stop the stopwatch. Remember, the speed of sound is 1,000,000 times slower than the speed of light. Speed of light is 300 million meters per second. The speed of sound is just about 300 meters per second. 330, 340. If you're going to get the velocity of ripples on a water surface, you drop a pebble or use a ripple tank and it'll send waves out into the water. You'd have to measure the distance that the wave travels and measure the time that it took for the wave to travel, and then just do distance divided by time. Explain how waves will be refracted at a boundary in terms of the change of direction and speed. So if I have a look down here, this is light wave going into glass, which is more dense. So the wave slows down, and as it does, it bends toward the normal. And then when the light comes out of the glass back into air, which is less dense and easier to travel through, the wave speeds up and it's going to bend away from the normal. So just remember, if it slows down, it bends toward the normal. If it speeds up, it bends away from the normal. And the normal is an imaginary line that we draw at 90 degrees in order to see what the angle is between the ray and the normal, so we can compare. I is angle of incidence, R is angle of refraction. Higher tier candidates need to recall that different substances may absorb, transmit, refract or reflect waves in ways that vary with wavelength. So first of all, let's make sure we know what those mean. So refract means bend, reflect means bounce, transmit means to pass through, and absorb means to go in and doesn't come out. So the energy will get trapped inside the material and the material will probably heat up a little bit. It's only worth 1 mark, so that'll do for that. Higher tier candidates don't need to know about the core practical. I will explain it on the foundation video though, because foundation candidates do need to know about it. Unit SP5, light and the electromagnetic spectrum. So you can see the higher candidates only need to know little bits about this. Foundation candidates need to know the similar bits but in perhaps a little bit more detail. Recall that all electromagnetic waves are transverse, that they travel at the same speed in a vacuum. 1 mark for saying electromagnetic waves are transverse, and another mark for saying they travel at the same speed in a vacuum. Explain with examples that all electromagnetic waves transfer energy from source to observer. So it's only worth 1 mark, so you just need to know that statement. So all of these waves here transfer energy. We don't need to know the core practical. Recall the main groupings of the continuous electromagnetic spectrum in order. So here they are. You got radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. Describe the electromagnetic spectrum as continuous from radio to gamma, and that the radiations within it can be grouped in order of decrease in wavelength and increase in frequency. Well, any wave over here have got long wavelengths, they've got low frequency, and they've got low energy. And they are the least dangerous. And as you move across the spectrum, the wavelength gets shorter and shorter and shorter, and the frequency gets higher and higher and higher. And as it said, it's a continuous spectrum. Over on this side here are the waves with the short wavelengths, high frequency and high energy, and they are the most dangerous. Recall that the potential danger associated with an electromagnetic wave increases with increased frequency. Yeah, well, I've just covered that. Over here they've got a low frequency, so the waves haven't got much energy. Over here the waves are vibrating a lot and they've got a lot of energy. That's the way I like to think about it. So they're the most dangerous over on this side here. Describe the harmful effects on people of excessive exposure to electromagnetic radiation, including, so you've got to know that microwaves can cause internal heating of your body cells. In other words, cooks you from the inside. Infrared waves can cause skin burns. Infrared is just a posh word for heat. So you know that if you get too close to a fire, lots of infrared is coming off a fire and it can burn you. Ultraviolet does damage to surface cells and eyes. So surface cells just is like your skin cells. So too much sun can damage your eyes and it can damage your skin. It could lead to skin cancer and eye conditions. So be specific. If it asks about ultraviolet, don't just say it causes cancer, say it causes skin cancer. Because ultraviolet can't penetrate inside the body, it just lands on the skin. X-rays and gamma rays, the dangers, they could mutate or damage your cells in your body, and that could cause cancer. So don't just say X-rays and gamma rays could cause cancer. Say they damage your cells. You could even say damages the DNA of cells for 1 mark and then causes cancer for another mark. Describe some uses of electromagnetic radiation. Radio waves are used for communications. I wouldn't say in satellite transmissions. I would leave that for microwaves. Microwaves are what we use to communicate more often with satellites, and also microwaves are used for cooking. Infrared waves is also used for cooking. Remember, infrared's just heat. It's thermal imaging, so infrared goggles, and we use infrared for TV remote controls. Visible light, well, anything to do with vision, so photography or watching the telly, the TV screen, you wouldn't be able to do it if there was no visible light coming off. Ultraviolet, we'll use it for security marking and for detecting forged banknotes. X-rays, well, medical X-rays for checking for broken bones, but you could also look inside any object, such as airport security scanners for looking inside your luggage. And gamma rays, we use those to sterilise food and medical equipment. And we also use it to detect cancer and treat cancer. Higher candidates need to know this. Foundation candidates don't. Recall that radio waves can be produced by or can themselves induce oscillations in electrical circuits. In other words, for 1 mark, radio waves can cause electrons to oscillate backwards and forwards in a circuit, and you can also use aerials to transmit those oscillations through the air and then be received at the other end, and those oscillations will make the electrons in the aerial oscillate at the far side where they're being detected. Recall that changes in atoms and nuclei, so that just means the particles that's in the nucleus, can generate radiations and be caused by absorption of radiation. So in other words, when the nucleus of an atom changes, it can give off radiation. And also, if the atom absorbs radiation, it can basically cause the nuclei in the atom, to rearrange. And the last unit for foundation and higher candidates is SP6 Radioactivity. And you can see here, once again, it's very, very similar. The only difference being, higher candidates need to know a little bit more detail when it comes to these statements here. Describe an atom as a positively charged nucleus consisting of protons and neutrons surrounded by negatively charged electrons, with the nuclear radius much smaller than that of the atom, and with almost all of the mass in the nucleus. So for just 1 mark, that's basically everything you need to know. We don't need to go beyond that. So it's just a statement in itself. You've got to be able to recall the typical size of atoms and small molecules. So if we say that an atom radius was 1 × 10⁻⁻10 meters, make sure you know that value, because that could be worth 1 mark in an exam. If you've got a molecule, that could be 3 atoms joined together. So in other words, it's 3 × 10⁻⁻10. And the radius of the nucleus is 100,000 times smaller than the radius of the atom, approximately. So that'll be 1 × 10⁻15. So make sure that you know these values. It'll probably only be worth 1 mark in a multiple choice question, but we want to get all of these extra little 1 marks, because every time you get an extra 6 marks, roughly, that's you going up an extra level. Describe the structure of nuclei of isotopes using the terms atomic or proton number and mass or nucleon number, and using symbols in the format. So this bottom number here is the atomic number or proton number, and the top number is the mass number. So this is how you'll commonly see it, like that. with the letter C in between the two numbers. Recall that the nucleus of each element has a characteristic positive charge, but that elements differ in mass by having different numbers of neutrons. In other words, the definition of an isotope for 2 marks in an exam, you've got to say an isotope has got the same number of protons but a different number of neutrons. Remember, it's the number of protons on the bottom that define what element it is, but the mass number on the top can change depending on how many neutrons it's got. Recall the relative masses and relative electric charges of protons, neutrons, electrons and positrons. So there's the particles there. Here's their relative masses and their relative charges. So a proton's got a relative mass of 1, so is a neutron. An electron is nearly 2,000 times lighter, so is a positron. And the relative charges, proton is positive, neutron is neutral, electron is negative, and a positron is positive. That number there is 1 divided by 1,835 if you want to be exact. Recall that in each atom, its electrons orbit the nucleus at different set distances from the nucleus in shells. So that's your standard picture, which I'm sure you have saw before. Explain that electrons change orbit when there is an absorption or emission of electromagnetic radiation. Well, if an electron absorbs energy, it'll jump up a shell, and if it emits energy, it'll drop down a shell. Explain how atoms may form positive ions by losing outer electrons. So if one of these electrons were to absorb so much energy, it'd have enough energy to completely leave the atom, and that's what we call an ion. Recall that alpha, beta minus, beta positive, positron, and gamma rays and neutron radiation are emitted from unstable nuclei in a random process. So basically, all of these different types of radiation come from the nucleus of an atom, and we can never tell when they're going to come out because radioactive decay is random. Recall that alpha, beta minus, beta plus, and gamma rays are ionizing radiations. What does that mean? It means they can remove electrons from atoms if they bump into the electron. Explain what's meant by background radiation. Well, it just means radiation in the environment, all around us, all of the time. There's nothing we can do about it. Describe methods for measuring and detecting radioactivity limited to photographic film and a Geiger-Müller tube. Well, a Geiger-Müller tube that would click when it detects radioactivity, and a photographic film would turn from transparent to black. So the darker it is, the more radiation you've been exposed to. Recall that an alpha particle is equivalent to a helium nucleus, which is here, helium nucleus. So it's helium but without the electrons. A beta particle is an electron emitted from the nucleus. There's your beta there. So 0 mass and a charge of -1, so it's basically a fast-moving electron. And a gamma ray is electromagnetic radiation. So it's just pure energy, no mass, no charge. And all of these come out of the nucleus randomly. Compare alpha, beta and gamma radiations in terms of their abilities to penetrate and ionize. So the penetration power of gamma is high, beta minus is medium, and alpha is low. So remember, alpha gets stopped by paper, beta gets stopped by thin sheet of aluminium, and gamma, you need a thick sheet of lead, or meters and meters thick of concrete. The ionization power, well, gamma is the lowest ionizer, beta is the medium ionizer, and alpha is the high ionizer. So a high ionization power. In other words, alpha can knock off electrons from an atom easy. Beta struggles a little bit because it's so small, and gamma, well, gamma doesn't have any mass, so that's going to be very difficult just to knock it off. It's got no charge either. And finally, you can see here for higher and for foundation, you need to know everything. Higher need to know these statements in a little bit more detail. Foundation need to know these statements in a little bit more detail. But apart from that, they're very similar. Describe how and why the atomic model has changed over time, including reference to the plum pudding model and Rutherford alpha particle scattering leading to the Bohr model. So, first of all, we just started off as an atom, Dalton's model, and then we had the plum pudding model when J.J. Thomson came along and discovered the electron. So the plum pudding model is basically where the atom has a positive charge and it's got little negative charges spread out all over the place, localized. And then Rutherford came along with his gold leaf experiment, his alpha scattering experiment, and he discovered the nucleus. So we had most of the mass of the atom was in the middle. Niels Bohr came along and discovered that the electrons orbited in shells around the outside. I've got a nice little video all to do with the history of the atom. Check it out if you don't really know what I'm talking about there. Describe the process of beta minus decay, which is when a neutron becomes a proton plus an electron. So I've drew it out to try to help you. So that's your neutron there becoming a proton and the beta minus. Remember, these top numbers on the right of the arrow have to equal the top number on the left of the arrow, and these numbers on the bottom on the right of the arrow have to equal the number on the bottom on the left of the arrow. So 1 plus minus 1 equals 0, and 1 plus 0 equals 1. So that's the mass number on the top and the charge number on the bottom. Describe the process of beta plus decay. So that's when a proton becomes a neutron plus a positron. So this is the proton splitting up this time into a neutron and beta plus. Explain the effects on the atomic or proton number and mass or nucleon number of radioactive decays, alpha, beta, gamma and neutron emission. So if a radioactive nuclei decays and gives off alpha, the atomic number is going to decrease by 2. So remember, the atomic number is the bottom number. So alpha's got 2 protons in, so that's why the atomic number decreases by 2, because the atomic number is the proton number. The mass number is going to decrease by 4 because an alpha is 2 protons and 2 neutrons. Each one of those particles have got a mass of 1, so that's a mass of 4 in total. Beta minus, the atomic number is going to increase by 1. That's because a neutron turns into a proton. There's no change in the mass. That's because the proton stays in the nucleus, just takes the neutron's place. The gamma, there's going to be no change in either the atomic number or the mass number. That's because gamma doesn't have any mass and doesn't have any charge. It's just pure energy. It just gets released to help to rearrange the nuclei in the nucleus so it becomes more stable. And if a neutron is given off, there's no change in the atomic number, because the atomic number is just the proton. However, the mass number will decrease by 1 because a neutron has got a mass of 1, and you're kicking it out. Recall that nuclei that have undergone radioactive decay often undergo nuclear rearrangement with a loss of energy as gamma radiation. Use given data to balance nuclear equations in terms of mass and charge. So I've given an example here. You've got radium 22688 turned into radon after kicking out an alpha. So 222 plus 4 equals 226. So that means, yes, the mass numbers balance. And 86 plus 2 equals 88. So that means that the charge number balances as well, or the proton number. Describe how the activity of a radioactive source decreases over a period of time. That's just a statement. So activity gets less as time ticks by. So in other words, it's not as radioactive anymore. Recall that the unit of activity is the becquerel. So 1 mark for knowing that. BQ. Explain that the half-life of a radioactive isotope is the time taken for half the undecayed nuclei to decay, or, my personal favourite, the time taken for the activity of a source to decay by half. Well, a nice little video all to do with half-life if you don't really know what's going on with half-life. Explain that it cannot be predicted when a particular nucleus will decay, but half-life enables the activity of a very large number of nuclei to be predicted. Use the concept of half-life to carry out simple calculations on the decay of a radioactive isotope, including graphical representations. If you don't know what that means, you'd better check out my video, as I've just said. So this is your activity at a time of 0. The activity was initially 80, and over time the activity decreases. So the radioactive source is not as radioactive anymore. The amount of time that it took for the activity to half, well, half of 80 is 40, so in this case 10 minutes. So the half-life is 10 minutes. Remember, you can also describe half-life in terms of the time it takes for the number of undecayed nuclei to half, not just the activity to half. So we could use this graph here. You've got 1,000 undecayed nuclei at first. What's half of 1,000? 500. Right, how long did it take to go from 1,000 to 500? 10 minutes, right? As you come down the graph like that, always do little dotted lines coming out across here, little dotted lines going down. The examiner will understand that you know what you're doing as soon as they see those little dotted lines. Describe the dangers of ionizing radiation in terms of tissue damage and possible mutations, and relate this to precautions needed. So the dangers obviously are tissue damage for 1 mark, possible mutation of cells for another mark. Precautions needed, well, if you've got to be next to a radioactive source, minimise the amount of time that you spend close to it. Stay away from it as much as you can. Handle it with tongs. Wear a lead apron or shielding behind some lead glass or something like that. Wear a dosimeter badge to record your exposure. So they are all good ways of decreasing your exposure. Explain the precautions taken to ensure the safety of people exposed to radiation, including limiting the dose for patients and the risk to medical personnel. Well, I've just been over those precautions, so it's the same again. And finally, describe the differences between contamination and irradiation and compare the hazards associated with the two. So contamination means you have particles of radiation on you or in you. That's very dangerous, especially if they're in you, because you can't get away from them. So it's a very high hazard. Irradiation, the hazard's not as big. If you've been irradiated, it means you were exposed because you were close to a radioactive source. However, once you move away from the source, then the irradiation stops. So that's not as dangerous as being contaminated. And there we go. So the intention of this video is for you to be able to spot any weaknesses that you've got. The document shows you exactly what you're going to be tested on. Okay? So if you go away now and make sure that anything that you're struggling with, do something about it. Become a better version of you and increase your success. Work hard. Be nice. Bye for now.